Hello dear students, welcome to Score Booster series GATE 2026. Myself Somashekar, faculty at ACE Engineering Academy. I teach subject reinforced cement concrete. Here I will give some of the best questions for GATE 2026 numerical answer type and MSQ. Let us see the first question from this series. Which of the following is a long-term loss? Options given: A. Shrinkage of concrete, B. Creep of concrete, C. Elastic deformation of concrete, D. Relaxation of stress in steel. My dear, losses are of two types, which are immediate losses and time dependent losses, or you can say long term losses. Immediate losses and time dependent losses. Immediate losses and time dependent losses. Under immediate losses, one is elastic deformation of concrete, loss due to elastic deformation of concrete. Elastic deformation of concrete. Second one, loss due to anchorage slip. Loss due to anchorage slip. And next one, loss due to friction. These are immediate losses. Easily you can pick up the options now. Anyway, come to time dependent losses. Loss due to shrinkage of concrete. Loss due to shrinkage of concrete. Then loss due to creep of concrete. Loss due to creep of concrete. Then loss due to relaxation of stress in steel. Loss due to relaxation of stress in steel. Okay. Here given options, long term losses we want. Shrinkage of concrete, yes, it is a long term loss. Creep of concrete, long term loss. Elastic deformation of concrete, it is immediate loss. Relaxation of stress in steel, also called a creep in steel. My dear, it is also a long term loss. So A, B, C is the answer for this question. A correct, B correct and D correct. I am sorry, D correct. A, B and D. For first question, A, B, D. MSQ. MSQ. Coming to the next question. Actual depth of neutral axis for a simply supported, singly reinforced rectangular beam in elastic method depends on which method? Elastic method, which is also called working stress method. In working stress method, for a singly reinforced beam, actual depth of neutral axis depends on options given: A. Geometry of the section, B. Concrete grade, C. Steel grade, D. Area of tension steel. My dear, first of all let me write actual depth of neutral axis. Actual depth of neutral axis. Actual depth of neutral axis, Bxa square by 2 equal to m times AST into D minus XA. Here XA depends on B, D, AST and M, where M equal to 280 upon 3 sigma CBC, where sigma CBC depends on concrete grade. Sigma CBC depends on concrete grade. B and T we call it as size of the beam or a geometry of the section. So A correct, it depends on geometry of the section, and M equals to 280 upon 3 sigma CBC, where sigma CBC depends on concrete grade. That means XA depends on concrete grade. B correct. Then C, steel grade. Here a steel grade not required to find actual depth of neutral axis. So C wrong. Then coming to AST, area of tension steel. So Correct answer is A, B and D. A, B and D. MSQ once again, right? Okay. Then move to next question. The effective length of a column in a reinforced concrete building frame as per IS 456-2000 is independent of options given: A, frame type, B, span of the beam, C, height of the column, D, loads acting on the frame. My dear, effective length of column. First let us check whether it depends on frame type or not. Consider one without sway. Consider same height of the column but with sway. Consider same column but with sway. But observe the effective length. For the first case, effective length is 0.65 L and for second case, effective length is 1.2 L. From this we can say effective length of column depends on frame type. Option A is correct. Then coming to the span of the beam, in a building frame, let us take a simple frame. This is the column, and this one be the beam. Height of column or length of column you can say, and the span of the beam. Here effective length depends upon beta 1 and beta 2. Effective length depends upon beta 1 and beta 2. Beta 1 and beta 2 depends upon summation of stiffness of column to summation of stiffness of column plus summation of stiffness of beam. Stiffness of beam in a frame, let us take it 4EI upon LB. For small span, stiffness different. For long span, stiffness different. So as the span of beam changes, then definitely effective length of column will change. Now effective length of column depends on span of the beam. B also correct. Coming to the next, C, height of the column. Let us take two different heights of column. One will have height L, the other will have height 2L. Let us take same supports but different height. For the first case, effective length will be 0.65 L. For the second case, effective length will be 0.65 into 2L. So you will get it is 1.3 L. From this you can say effective length depends upon height of the column. So height of column also correct answer. Coming to the option D, given that loads acting on the frame. My dear, it is not depending. Effective length of column is independent of loads acting on the frame. Now A correct, B correct, C correct. Again MSQ, A, B and C. Let us move to the next question. A RC column is said to be an axially loaded column. Then its least lateral dimension should not be less than. Axially loaded column from IS 456-2000 decided based on the condition E minimum should be less than or equals to 0.05 times least lateral dimension of column. When do you say that it is an axially loaded column? If E minimum less than or equals to 0.05 times least lateral dimension of column. Okay. Where E minimum consider in worst case 20 mm. Let us consider 20 mm. It should be less than or equals to, I can write down 0.05 as 1 by 20. Let us bring 20 to left hand side. You will get 20 into 20 mm less than or equal to B. Now simplify this, you will get 400 mm less than or equals to B. From this you can write B should be greater than or equals to 400 mm. Or you can write B should not be less than 400 mm. If you want to say it is an axially loaded column, then its least lateral dimension should be at least 400 mm, right? So correct answer is 400. Now answer is 400. Required in mm. So we are taking here 400. Sometimes they may ask in meters also. Okay. So please take care in numerical answer type question, units. Number 1, if available, take care of units, and number 2 is decimal places. Okay. Let us move to next question. If a two-legged 8 mm diameter HYST bar is used as a shear reinforcement for a beam of width 230 mm and effective depth 300 mm, the spacing of minimum shear reinforcement is, they are asking what is the spacing required for minimum shear reinforcement. My dear, spacing required for minimum shear reinforcement, spacing required for minimum shear reinforcement. That is ASV upon B into SV should be greater than or equal to 0.4 upon 0.87 Fy. ASV here given two-legged 8 mm diameter. So area will be 2 into pi by 4 into 8 square. We are getting area upon B is given that 230 mm. 230 into SV. It should be greater than or equal to 0.4 upon 0.87 Fy. Here grade of steel not given, but mentioned HYST bar. In HYST bars, my dear, we have different grades FE415, FE500, FE550, etc. Okay, but according to IS code, maximum grade of steel used for stirrups will be FE415. So from HYST bar, that is the least grade. So you can pick up FE415 for stirrups. Grade of steel for stirrups, you can pick up FE415. So simplify this value, you will get SV. SV should be less than or equal to how much? Let us simplify this. It is 0.87 Fy into ASV, 2 into pi by 4 into 8 square, that is 64 upon 230. My dear, upon 0.4. Yeah, it is 394 mm. It is 394 mm. We are getting 394 mm. But this spacing in any case not more than maximum spacing. You know, let us go for checklist. Check. First of all, you can write calculated spacing. Calculated spacing we are getting 394 mm. But the spacing in any case not more than maximum spacing, that is 0.75D or 300 mm, whichever is smaller. Now 0.75 into D value, here D given 300 mm, so 0.75 into 300, how much it is? 0.75 into 300, 225 mm, 225 mm. Finally, you can choose a smaller value. In this checklist, finally which value we can choose? We choose a smaller value. Here smaller value is 225 mm. So provide 225 mm. If 225 mm available, pick up. If not, nearest value you can pick up. Not a problem. But it is a numerical answer type, na? Definitely you need exact value. Okay. 225 mm. 225 mm is 225 mm. 225 mm. Okay. Right. The next question. For a simply supported, singly reinforced rectangular beam in limit state method, if the area of tension steel increases, then, okay, in limit state method, very clearly mentioned method, limit state method, okay. If area of tension steel increases, then options given A, depth of neutral axis increases. Let us check it whether it is correct or not. Depth of neutral axis we can write down XU equal to 0.87 Fy AST upon 0.36 FCK into B. Here XU and AST are directly proportional. When we increase AST, definitely XU value will also increase. So, depth of neutral axis increases. Option A is correct. Then coming to the option B, lever arm increases. My dear, lever arm Z equal to D minus 0.42 XU. Okay. Here as AST increases, XU increasing. As XU increases, Z decreases because here sign negative is there. Right, here negative sign is given. Due to this, the overall net value will be decreases, okay. But here given increases, so be wrong. Then coming to the next one, moment of resistance increases. You know, moment of resistance is 0.87 Fy AST into Z. 0.87 Fy into AST into Z. Here what happens when AST increases? AST and moment of resistance are directly proportional. As the AST increases, then definitely moment of resistance will also increases. It is true. True. Then what about option D? Ductility increases. My dear, as AST increases, XU increases. As XU increases, curvature decreases. As curvature decreases, then ductility decreases. Ductility decreases. But they have given ductility increases, so wrong. Ductility decreases. Ductility of the beam decreases with increase in tension steel. So, A correct and C correct. A correct and C correct. Option A and C. Option A and C. Okay. Moving to the next question. Yeah. For a rectangular section, width 230 mm and effective depth 500 mm. Then the effective cover to compression steel as 48 mm. Grade of concrete M20 and grade of steel Fe415. The strain in compression steel in beam for balanced failure up to 1 decimal place is, my dear, they are asking strain in compression steel. Strain in compression steel will be for balanced failure, it is 0.0035 into 1 minus D dash upon XU max. It is the strain in compression steel for a balanced failure or for a balanced section. Okay, let us substitute the values now. 0.0035 into 1 minus, what is the D dash given here? 48 mm. 48 upon XU max. For Fe415 grade steel, XU max is 0.48 D. Let us substitute here 0.48 D. What is the effective depth given here? Effective depth given 500 mm. Let us substitute effective depth. Then simplify, you will get the answer. That is 48 upon 0.48 into 500. 1 minus answer into 0.0035. So, 2.8 into 10 power minus 3. Here mentioned up to 1 decimal place only. You can enter the value up to 1 decimal place only. So, 2.8 into 10 power minus 3 we are getting. Already they have given 10 power minus 3 here. Okay. So, enter the value 2.8, that will be the answer. Answer is 2.8. Okay, already they have given into 10 power minus 3. Okay. Fine. Moving to next question. The net downward load to be considered for the analysis of the prestressed concrete beam provided with a parabolic cable as shown in figure below is in kilonewton per meter is dash. What will be the net downward load? My dear, we know the downward load here 10 kilonewton per meter. Then what about the force acting upward direction due to prestress? Let us find the upward force. That is 8 pH upon L square. 8 P given here 500 kilonewton. H is given that 100 mm. Let us write in meters. 100 upon 1000 upon L square, where L given 10 meters. So 10 square. How much it is? 2 zeros gone, 1 by 10. Okay. So 8 into 500 into 1 by 10 upon 10 square means 100. Yeah, we are getting that it is a 4 kilonewton per meter. This is upward load or upward force. What is the downward force? 10 kilonewton per meter, including self weight. Okay. But the question is, what is the net downward load? Net downward load. Net downward load equal to 10 minus 4, 6 kilonewton per meter. So answer is 6. Answer is 6. Okay? Right. They have given parabolic cable. Due to parabolic cable, the force is acting like UDL due to prestressing effect. How much it is? We are getting 4 kilonewton per meter. Downward load 10, upward force is 4. So what is the net load? 10 minus 4. Okay? Good. Next question. In prestressed concrete, high grade concrete is used for. Why do we use high grade concrete or a high strength concrete? Options given here: A, having concrete of low ductility, having concrete of high brittleness, having low creep, having high modulus of elasticity of concrete. The main reason to select higher grade concrete in prestressed concrete is it will have low creep and it will have higher modulus of elasticity of concrete. You know modulus of elasticity? 5000 root FCK. So as a higher grade of concrete you select, definitely EC value will also be higher. So C and D is the answer. C and D. C and D. Okay, right. Next question. A simply supported rectangular beam of size 200 mm by 400 mm. A parabolic cable is provided with 0 eccentricity at supports and 50 mm at midspan. The pre-stressing force in the cable is 800 kilonewton. The stress in the concrete at bottom fiber at transfer, neglect self-weight of the beam at support in megapascal is dash. Okay, listen. Here they have mentioned that it is simply supported rectangular beam. Let us take a longitudinal section. And they have given that it is parabolic cable. It is having the force, how much it is given? 800 kilonewton. 800 kilonewton. and eccentricity given 0 at support and 50 mm at midspan. 50 mm at midspan. The pre-stressing force in the cable, okay, the stress in the concrete at bottom fiber at a transfer. At a transfer, what are the effects to be considered in analysis? My dear, at the time of transfer of pre-stress, we have to consider only two effects. One is self-weight of the member, another one is pre-stressing effect. But in the question clearly mentioned that neglect self-weight of the beam. If you neglect self-weight, then we have only pre-stressing effect, okay. Then where do you want the stress? I want the stress at bottom fiber, okay, at support. This location, they are asking at this location, at support at bottom fiber. My dear, at support, actually P by A is the stress due to pre-stressing effect, and P by Z and MD by Z. Here we can neglect MD by Z because it is mentioned very clearly, neglect self-weight. This term is due to self-weight. Even this is also make it to 0. Why? Because at support they are asking, at support eccentricity is 0. At midspan eccentricity is 50 mm, but at support eccentricity is 0. So, only P by A be the stress. Whether you take at bottom fiber or you take at the top fiber, the stress will be simply P by A only. Now, stress at bottom fiber they asked, stress at bottom fiber is P by A, where pre-stressing force P is 800 kilonewton. Let us write in Newton upon size of the beam given that 200 mm by 400 mm. So, how much it is? Here 3 to 5 zeros, here 4 zeros, okay, 4 zeros gone, 8, I think you will get 10, is it right? Check it once, 800 into 10 cube upon 200 into 400. Yeah, it is 10 Newton per mm square or 10 megapascal. We want answer in megapascal. Yes, we are getting in megapascal only, right? So, answer is 10. For this question, answer is 10. You must check it. Where do we find the stress? Whether it is at support or is it at midspan, okay? Next, you want the stress in megapascal or in kilopascal. Check this point. Next one, did any condition mentioned in the question? You need to check this one also, right? If no condition given, well and good, you need to consider what are the effects available at a transfer stage. But here clearly mentioned that neglect self-weight of the beam. That is why we are going to neglect the self-weight term, okay na? Right. So, answer is 10 for this question. Then moving to next question. The ultimate load carrying capacity of a circular section of 400 mm diameter, okay, diameter given 400 mm with a helical reinforcement. Actually, in circular column, we can provide either lateral ties or a helical reinforcement. Here clearly mentioned that we are using helical reinforcement, okay. Using 1% of longitudinal steel, yeah, they have given that 1% longitudinal steel, given that 1%. Concrete grade M20, so FCK we can take it as a 20, and steel grade of Fe 415, so we take it Fy as a 415 Newton per mm square. Answer required in kilonewton, round off to nearest integer, okay. They are asking ultimate load carrying capacity. This word refers use a balanced section, right. If it is a working stress method, simply they ask a safe load carrying capacity of column or safe load carried by the column, okay. when they mentioned ultimate load or factor load, immediately you understand this question is from limit state method. Okay, right. For a circular column with a helical reinforcement carried by load, how much? 1.05 into 0.4 FCK AC plus 0.67 Fy into ASC. That is 1.05 into 0.4 FCK. Here FCK be the 20 into AC, where AC be the net area of concrete, which is gross area minus area of longitudinal steel. Gross area, since it is circular column, we can write it is pi by 4 into diameter square minus area of longitudinal steel given in the question 1% of gross cross-sectional area plus 0.67 Fy into ASC. Right. Now, simplify this, you will get the answer. What is the value? 1 upon 100, 1 minus answer into pi by 4 into 400 square into 0.4 into 20 plus 0.67 into Fy into ASC. It is 1% of pi by 4 into 400 square. Into 1.05. I am getting here 1411.89 into 10 power 3 Newton. But we want answer in kilonewton, that to round off to nearest integer. So, let us take it 141, next decimal is more than 5. So, I can write down 1412 kilonewton. 1412 kilonewton. Now, answer is 1412. Answer is 1412. 1412. Is it okay? They are asking ultimate load carrying capacity of a column for a helically reinforced column. Okay. Moving to next question. For a simply supported pre-stressed concrete beam of span 12 meters, the upward deflection in mm in integer of a beam should not be more than. My dear, they are asking upward deflection. This upward deflection of a pre-stressed concrete member in any case not more than span upon 300. Vertically downward deflection different, upward deflection different. Okay. Here they are asking upward deflection, that is not more than span is 12 meters. So, it is 12,000 upon 300. 2 zeros gone. So, it should not be greater than 40 mm. It should not be greater than 40 mm. We want answer in mm. We want answer in integer. Already we are getting integer only, not a problem. So, 40 is the answer. For this question, answer is 40. Maybe you can expect downward deflection. The downward deflection is not more than span upon 250. One condition is this. Other condition is deflection should not be more than span upon 350 or 20 mm, whichever is smaller. My dear, these two conditions valid in RCC as well as in PSC, but this condition valid only in prestressed concrete. When do we use this condition? My dear, whenever you take loads and secondary effects, loads and secondary effects. Loads produce some deflection, secondary effects also produce some deflection. If you take sum of this deflection, it should not be more than span upon 250. Then when do we use the second condition here? The second condition we can use only under secondary effects. Only under secondary effects. The secondary effects like shrinkage, creep, temperature change, etc. Okay, right. So these three conditions are important. Next question. The development length in compression for a 16 mm diameter deformed bar of grade Fe 500 embedded in a concrete of grade M20. The design bond stress is 1.2 megapascal in mm, in integer is a dash. They are asking development length. Development length mathematically we can determine like this: 5 into sigma st upon 4 times tau bd, or you can write 5 into sigma st in limit state method, we can write 0.87 Fy upon 4 times tau bd. Phi is bar diameter. Here given bar diameter 16 mm, given 16 mm into 0.87 Fy. Here steel grade given Fe 500, so Fy value as 500 upon 4 into, since it is a HYST bar, increase tau bd by 60%. Okay. And they are asking development length in compression. Development length in compression. So increase tau bd by 25%. Where tau bd, actual tau bd is 1.2. This tau bd increased by 60% because it is a HYST bar, and increased further 25% because we are calculating in compression zone. Then how much is it? This value we want. It is 16 into 0.87 into Fi 500 upon 4 into 1.6 into 1.25 into 1.2. I am getting 725 mm. 725 mm. Yes, we want answer in mm. Yes, we are getting in mm only. But integer required. Yeah, we are getting integer only. So answer is 725. Answer is 725. Is it okay? Right. Next question. A square footing of side 1 meters. They have given side of square footing 1 meter supports a square column of side 500 mm. Side of column given 500 mm. SBC of soil is 3 megapascal. SBC of soil is 3 megapascal. Concrete grade used M20. The depth of footing in mm is a dash. What is the depth of the footing required? It is the footing supporting to a column and it is resting on soil, so it exerts soil pressure. It exerts soil pressure. Say SBC of soil is Q0. They are asking what is the depth of footing required. Depth of footing required. My dear, we can find this angle, right? This angle we can find. How? Tan alpha should not be less than 0.9 times root over 100 Q naught upon FCK plus 1. It should not be less than 0.9 times root over 100 Q naught. What is Q naught here? 3 megapascal upon, what is FCK here? 20 plus 1. 20 1s are 20 5s are 5 into 3 15 plus 1 16 root 16 4 4 into 0.9 3.6. It should be greater than or equals to 3.6. Once you find this angle, then you can find this height. How? Because we know this distance. Even we know this distance. From this we can find this distance. What is this distance? I want to know this distance. It is capital B by 2 minus small b by 2, correct na? Exactly center is capital B by 2. From here to here small b by 2. But I want from here to here, that is capital B by 2 minus small b by 2. Let us write now tan alpha equals to d upon capital B by 2 minus small b by 2. Now what is d equal to from this? D equal to capital B by 2 minus small b by 2 into tan alpha. Let us write capital B 1 meter, small b 500 mm. Let us write in meters 0.5 by 2 into tan alpha 3.6. So how much you are getting? 0.25 into 3.6. We are getting 0.9 meters. 0.9 meters. But required answer in mm. Let us multiply with 1000. You will get 900 mm. 1 meter equals to 1000 mm. So multiply with 1000. You will get 900 mm. For this question, answer is 900. For this question, answer is 900. Okay? Right. Next question. A footbridge is used as a walkway. The beam is simply supported with an effective span of 18 meters. Okay, effective span given 18 meters. The effective width of flange in mm for the section given below is, okay, here in figure given details, okay. We want effective width of flange, okay, effective width of flange. In the question it is given footbridge. Footbridge is an example for isolated T-beam. For isolated T-beam, effective width of flange is L0 upon B plus 4 plus BW, which is not more than actual width of the flange. Let us find here L0. L0 is nothing but distance between zero moments. Here given that it is simply supported. My dear, for a simply supported beam, L0 equal to effective span. Here effective span given 18 meters. So 18 upon B, actual width of the flange is given 1800 mm, write in meters, plus 4 plus BW given here 300 mm, write in meters. So how much we are getting? 18 upon 1.8 plus 4. So 18 by, okay, plus 0.3. So I am getting 1.585 meters, 585 meters into 1000. Let us take into 1000. So we get 1585.7 85.7 mm. Okay, but we want integer. Let us say 1586 mm. 1586 mm. Let us compare with the actual width of the flange. This is the actual width of flange. My dear, it is less than actual width of the flange, therefore, okay, we can use it effective width of flange as 1586 mm. Suppose if the calculated effective width of flange is getting more than actual width of flange, in that case we can take effective width of flange is equal to actual width of the flange. Okay, right. Next one, next question. For this question, what is the answer? Answer is 1586. 1586 is the answer. Move to next question. The height of sample sand to be tested is 20 centimeters. Okay, height of sand H1 20 centimeters, and the height of the saturated sand is 16 centimeter. That means it is H2. H2. The percentage of bulking is a dash. Okay, let us take it. It is H1 minus H2 upon H2 into 100. You will get percentage of bulking. H1 20 minus 16 upon 16 into 100. So, you will get 4 upon 16, right? It is 4 upon 16 into 100. You will get 4 ones are 4 fours are 25%, you will get it. 25 is the answer. They want in percentage directly, so 25 is the answer. 25 is the answer. Okay, right. Next question. The percentage of the fine aggregate of fineness modulus 2.6. Okay, this is the percentage of fineness modulus of fine aggregate. Let us say it is P1 to be combined with a coarse aggregate of fineness modulus 6.8. Okay, let us take this value as a P2. For obtaining the aggregates of fineness modulus is 5.4. Okay, so it is considered as P. Now we want percentage of the fine aggregate, right? That is P2 minus P upon P minus P1 into 100. P2, how much? It is 6.8 minus 5.4 upon 5.4 minus 2.6 into 100. So, how much it is? 6.8 minus 5.4 upon 5.4 minus 2.6 into 100. So, we are getting 50. So, correct answer is 50. Answer is 50. Okay. Then moving to next question. Which of the following is a Bogue's compound? Here given tricalcium silicate, nothing but C3S, dicalcium silicate, nothing but C2S, tricalcium aluminate, C3A, dicalcium aluminate. There is no compound like this. C3S, C2S, C3A and C4AF. These four are Bogue's compounds. C4AF is a tetracalcium aluminoferrite. So, A is a Bogue's compound, B is a Bogue's compound, C also a Bogue's compound, but D is not a Bogue's compound. Answer is A, comma B and C. A, comma B and C. Okay, right. Coming to the next one. A simply supported, singly reinforced rectangular beam of span 15 meters. Okay, span of the beam given that 15 meters. The modification factor for tension steel, so gamma value given 1.5. The effective depth of beam in mm required to satisfy the vertical deflection limit is, my dear, to satisfy vertical deflection limit we can take L by D permissible, that is alpha, beta, gamma, delta and lambda. Here alpha equal to, beta equals to, gamma equals to, delta equals to, lambda equals to. They have mentioned that a rectangular beam. For rectangular cross section, lambda equals to 1. From the graph, lambda equals to 1 for rectangular cross section. And they have given that it is singly reinforced. For singly reinforced sections, delta equals to 1 from the graph. From the graph which is given in IS 456-2000. Then gamma they have given, modification factor for the tension steel they have given. Then what about beta? Here span of the beam is given 15 meters. So let us take 10 upon span. It is more than 10 meters na. So we can write 10 upon span into, for which one? Simply supported. Let us take 20. Then what about alpha? If span is more than 10 meters, alpha equals to 1. Okay. Now substitute here. Alpha 1, beta 10 upon span is 15 into 20 into gamma 1.5, delta 1, lambda 1. Okay. Now simplify, what will you get? 15, 15 gone. L by D equals to 20. Okay. From this, what is D? D equals to L upon 20, where L is how much? Where L is 15. So 15 by 20, you'll get 0.75 meters. But they want answer in mm. Let us take it 750 mm. 750 mm. So answer is 750. Answer is 750. Actually, you can find the depth to resist the moment. That is for a design. But here they are asking for serviceability criteria. Under serviceability, you get the deflection. To satisfy the vertical deflection limit, what may be the minimum depth required? My dear, we can find from L by D. If they asked for design, then we can equate mu to mu limit. Okay, right. Answer is 750. Then moving to next question. Which of the following is a governing factor to decide the design depth of RC footing? My dear, to decide the design depth of footing, we can use maximum bending moment. From this we get a certain depth. We use one-way shear, we get certain depth. We use punching shear, we get certain depth. From these three, you get depth, you get depth, you get depth. We will choose a maximum value. Among the three conditions, we will choose a maximum value. So, design depth of footing is decided based on three conditions: maximum bending moment, one-way shear force and punching shear force. From these three conditions, we get depth. Finally, we can choose the maximum value, because if we select the maximum value, it will satisfy other two conditions also. Okay, right. Yeah. So, from this subject, my dear, you can expect questions, mostly numerical. I think maybe from construction materials. From there, you can expect a theoretical question. But here, in RCC as well as in PSC, you will expect mostly numerical questions. Okay. I hope you have understood clearly, right? I wish you all the best for your GATE exam. Thank you.